Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022 that's available on Amazon.com, both in Kindle and in paperback. You can buy any one of these three volumes or any combination thereof. I think it's a good buy. You might want to check it out. But anyway, I'm doing this continuing feature on YouTube, and my videos you don't have to pay for. You can still. I'm going to eventually go over everything in the first two volumes. And right now I'm talking about functions, which is section 5.5 of volume one. This is my third video on functions. Today I'm going to talk about inverse functions and the identity function. So anyway, let's begin. So what is an inverse? Well, it turns out that not every function has an inverse. As a matter of fact, the only type of functions technically that have an inverse are bijections. And yesterday I talked about bijections. Those are just functions that are both one-to-one and onto. They're both injections and surjections. So if f is any bijection, then we'd say the inverse of f. So if we write y equals f of x, then the inverse of f, which we write as f with a superscript minus 1 to the right of it, we would say f inverse of y. We would say x equals f inverse of y. It's just a function that undoes the action of f. Remember, if you think of a function like a machine, a machine has an input and an output. So f is some machine that you start with some input x and it gives you some output y is equal to f of x. Well, the inverse of that would be a function if you gave it y, which is f of x, it would spit back out x, which is the thing you started with f. So if you like, but if you can compose these functions, I haven't talked about composition yet, but if you calculated f of f inverse of x, you would get back x. Similarly, if you calculated f inverse of f of x, that's equal to x. That's another way you can define an inverse of a function. And I think it's worthwhile just to go over some examples. So for the first example, suppose f is a function from the non-negative reals, which I'm writing as the interval from 0 to infinity, closed on the left. That means it includes 0, but it doesn't include infinity because infinity is not a number. It's not a real number. What this means is that it includes every positive number, no matter how large, every number that approaches infinity. So that's both the domain and range of f. And f is just a function such that f of x is x to the n, where n is some non-negative integer, some fixed non-negative integer. So for instance, f of x could be x, it could be x squared, x cubed, x to the fourth, any positive power of x. We don't really care what that power is, but it's some fixed integer, which we're calling n. So now we want to calculate the inverse of f. So the way we do that is we start by saying y equals f of x. So in this case, y is equal to x to the nth power. And now we want to try to solve for x in terms of y. Well, this is pretty straightforward because I think you can see that if you take the nth root of both sides of this equation, the nth root of an nth power gives you back the thing you started with. It gives you back x. It wouldn't really do this if x wasn't restricted to be non-negative, though. I mean, remember what I was saying about even powers? If n was an even integer and we weren't restricting the domain to be non-negative reals, they were letting be all reals, then I think you know there's two square roots, or in general, there's going to be two nth roots, one positive, one negative, whenever n is even. But here, since we're restricting our domain and our range to be non-negative, there is a unique inverse for every value of n. It's just the nth root. So that's a pretty straightforward example. Let's do another example. Suppose now we're letting the domain and the range be all the real numbers. And now we're letting m be an arbitrary non-zero real number. And we're saying f of x is mx. If you like, the graph of this function is just a line with slope m passing through the origin. And so in order to find the inverse, we say y equals mx. But then we just, to solve for x, as I think it's pretty clear, you just divide both sides of that equation by m, which you can only do if m is non-zero, because you can never divide by 0. But as long as m is non-zero, we can divide both sides by m, and when you do that, you get x equals y over m. So that's the inverse of this function, f inverse of x, you would say, is x over m. And by the way, it doesn't matter what name you give your variable for a function. If it's a univariate function, which this is a function of one variable, it doesn't matter what name you give that variable. So, right now we're writing, and I think I read in my book, f inverse of y is y over m. We might as well have written f inverse of x is x over m. Anyway. So now for the third example, this is similar. This one's a little bit more complicated. Suppose your function is f of x equals mx plus b, where again m is a non-zero real number and b is an arbitrary real number. You guys probably recognize this formula. This is just a formula for an arbitrary line, y equals mx plus b. Not quite arbitrary, because in this case we're requiring that m is non-zero, meaning it's not a horizontal line. A horizontal line is a function, but it's not a bijection, because it only has one value of x, or y, for every value of x. But as long as m is non-zero, you do get a function. And the only other line that doesn't have this form is a vertical line, which isn't even a function. But anyway, so we have a line that's not vertical or horizontal, given by f of x, which is y, is equal to mx plus b. And now we want to solve for x in terms of y. Well, this will require one additional step. So the first thing we do is we subtract b from both sides. So we're going to get y minus b equals mx. And now finally, to solve for x, we divide both sides by m. So I think you'll see you get x equals y minus b over m. That means f inverse of y is the function, it's the fraction y minus b in the numerator and m in the denominator. So that's the inverse of mx plus b, which is another equation of a line. Shouldn't be too much of a surprise. Okay, so just two more examples. Suppose f is now a function from all the non-zero reals to itself. So the way we write that, remember when I was talking about exclusion, complements. So this would be the complement of the singleton zero in R, which is just all the real numbers except for zero. So that's our domain and our range. And now our function f of x is 1 over x. And I think you can see why we have to include 0, because 0 doesn't have a reciprocal. You can't divide by 0. So what's the inverse of this function? We do the same thing. We say y equals 1 over x. Well, I think it's pretty clear. You can take the reciprocal of both sides of this equation. You just get x equals 1 over y. So in this case, we have f inverse of y is 1 over y. And it doesn't matter what name you give the variable. It might as well have written f inverse of x is 1 over x. But that's just what we started with. So this is a special type of function. This is a function that's equal to its own inverse. These are kind of rare. And this is a very important function, by the way. This is an example of a hyperbola. If you graph this function, you've probably seen this in high school. But this is a hyperbola, and I think you guys probably know, if you know about hyperbolas, they always have two branches, and they have two asymptotes. And in the case of the hyperbola y equals 1 over x, which you can also write as xy equals 1, the asymptotes are just the coordinate axes, the x and y axis, and the branches, there's one branch in the first quadrant, and there's another branch, which is a reflection in the third quadrant. I didn't include a graph here, but it's a pretty easy function to graph. So that's the fourth example. For my fifth and final example, I believe I went over this one yesterday. This is f of x equals square root of 1 minus x squared. And now the domain and the range we're using are the closed unit interval, just the closed interval from 0 to 1, which we write with brackets. And let's just do the work, the math, to calculate the inverse of this function. So we have y equals square root of 1 minus x squared. So we can square both sides. Then you get y squared equals 1 minus x squared. Now you can add x squared to both sides. You get x squared plus y squared equals 1. You guys should recognize that equation. That's just the equation of the unit circle. But actually, this is going to be a quarter circle. This function looks like a quarter circle. Just the quarter of the unit circle that's in the first quadrant. And the reason it's just that quarter is because, remember, we're restricting the domain and range to be non-negative, all numbers from 0 to 1, including 0 and 1. That's just the first quadrant of this unit circle. So we have x squared plus y squared equals 1. If you want to solve for x in terms of y, now you can subtract y squared from both sides. You get x squared equals 1 minus y squared. Final step is you take the square root of both sides. And ordinarily you would get two square roots, x equals plus or minus square root of 1 minus y squared. But we don't care about the negative square root in this case because we're restricting x to be non-negative. So we get x equals square root of 1 minus y squared. So f inverse of y is a square root of 1 minus y squared. Well, that's just the same function we started with. So again, this example is also an example where the function is equal to its own inverse. And by the way, functions that are equal to the own inverse, if you apply them twice, you get back the original. You just get x. And I'm just going to talk about one more thing now, the identity function. And the identity function, I think I already mentioned this one. It's a pretty boring function, probably the most boring function there is. It's a function that does nothing. F of x equals x. And no matter what your domain is, it turns out, there's always an identity function for any set. If x is any set, there's always a function from x to x that doesn't do anything. F of little x equals little x for every element. Little x is big X. If you remember, if you think of a function as a machine, this is the machine that doesn't do anything. Um, yeah, it's a boring function because it doesn't change your input. But it's important to acknowledge its existence. And I was talking about inverses a minute ago. If you apply f of f inverse of x is always x. So f composed with its inverse is always the identity. That's going to turn out to be a useful fact. And there are some particular functions that are equal to their own inverse. If you have a function that's equal to its own inverse, if you apply it twice, you get the identity. So anyway, it is a useful function, even though it's not really an interesting function. So anyway, that concludes my video for today on inverses and the identity function. Thank you for watching. Long live math, and I'll see you guys next time. Bye.